students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss some solved problems on error control codes. I already know that what is error control code and what are the types of error control codes already covered in theory. Now we are going to solve some problems on error control codes. Now error control codes are having two varieties. One is black codes and another is color codes. But according to syllabus, we are having black codes only, and cyclic codes are subclass of the black codes. So in error control codes part 1, we covered the black codes. Now we are going to part 2. In part 2, we are going to cover cyclic codes. Okay, so today problems on cyclic codes. So coming to the course outcome, this topic will come in module 5. So the module 5 is covered by 6th course outcome. What the 6th outcome says? Build the black codes for error detection and error correction in noisy environment. Already we know that why the error is arising. The error is arising in noise due to the noisy environment. So we are going to detect that error and going to correct that error. So that is about the black codes. So cyclic codes is nothing but a subclass of black codes. Okay. So coming to the problem. So the first problem, the generator polynomial for a 7,4 cyclic code is given by g of p is equal to 1 plus pq. Determine all the systematic and non-systematic code vectors. Here one thing, whereas in a black code, all the codes, that means all the message or the generator, all in matrix. So that's why it is in blocks. Whereas in cyclic code, where uses the polynomials. Here g of p, the generator polynomial is given as 1 plus pq, or in some textbooks 1 plus xq. Now this is g of x. So in this notation, the cyclic codes are appearing in this total syllabus. Okay. So what they ask? They go to find the code vectors in both the systematic and non-systematic. Okay. So now how to generate a cyclic code by using this generator polynomial. But here they are not given what the message vector or message polynomial. They are not given. They determine all the systematic and non-systematic code vectors. But there is a clue in this problem. What that 7,4? What is 7,4? Is nothing but in the form of n, k. It returns the length of the code. It returns the message block or message polynomial. Here, by comparing this n, k to the given 7,4, here you can say that n is 7, k is 4. It means the length of the code is 7-bit size, whereas the message is 4-bit size. Okay. So why? Because in previously we discussed about this black codes. So the black codes are in matrix form. So matrix form means here the k size starts from the k message starts from 4 zeros to up to 4 ones. Why? Because here again go to 2 power 4. What do you get 2 power 4? 16. So totally 16 code words are generated by using the given message. Why? From 000 to 1111. Totally having 16 message blocks. For the 16 message blocks, we can generate 16 code blocks in a black code. Similarly, in the cyclic code also, we can generate the 16 16 code polynomials by using the 16 message polynomials. Okay, so the first the given as generator polynomial. The given generator polynomial is nothing but 1 plus p plus p cube. Okay, so this is the generator polynomial. From this generator polynomial, we are going to generate the code polynomial. So you can say this is code polynomial. So all is in the form of polynomials. Okay, so out of 16 message polynomials, we can take any one for understanding, and then we go to find all the 16 code polynomials by using this message polynomials. Okay, for example, here I am taking one message polynomial is 1010 1010. So how can you enter this message polynomial from this message vector? So here 1 plus p option p square. So this is my message polynomial. Here you can see the first one digit 1, next p square, p cube. So this is my message polynomial. By using this message polynomial, I am going to generate the code polynomial. But here they are asking both the non-systematic and systematic code polynomial. So for these two varieties, we have a different procedure is there to generate. Okay, so first we go to the non-systematic polynomial. Okay, non-systematic polynomial. So the message polynomial is 1 plus p square, and the generated polynomial is 1 plus p cube. So here for the non-systematic cyclic code, here C of p, the code polynomial is generated by just multiplying the message polynomial with the generator polynomial. Message polynomial is multiplied with the generator polynomial. This is non-systematic. Okay. So what is my message polynomial? 1 plus p square and 1 plus p cube. Okay. So here we are going to multiply these two. So what do you get for 1 plus p cube, and second one is the p square. So we are going to multiply p square into 1 p square plus p cube plus p to the power of 5. Here you can see two p cube terms are there, not addition. Already you know that. What do we use? XOR operation. Okay. So again we go to write 1 plus p square plus p cube 1 XOR 1 plus p to the power of 5. So 1 XOR 1, what do you get? 0. So 0 into p cube, you get 0. So C of p is equal to 1 plus p square plus p to the power of 5. So this is my code polynomial in non-systematic form. For the non-systematic cyclic code, C of p is equal to. So again, you can write in the terms of code block. You're going to write. Okay. So what that my message? What is my code? 1 is there, p is there, p square, p cube is there? No. And p to the power of 4? No. And p to the power of 5 is there, and p to the power of 6 is opposite. So this is my code vector in terms of block code. So both are equal, but what are the difference? Whereas in block code, we are shown the message, the generator, and the code all in blocks, that is matrix form. Whereas in cyclic code, all are in polynomial form. 1 plus p or 1 plus x x square, like that, in that form. Okay, so this is the non-systematic. Why non-systematic says here we are using 1010 is the message, but this message not appears in this code. So yes or no? We can see the previous video. In that video, the black code generated. So the black code, we can see where the message, where the parity bits. Okay, but here we can't identify where this message. So this is the non-systematic. When you go for the systematic, again you can observe where the message. Okay, so that is the difference for the non-systematic and systematic. But all prefer the systematic only. Okay. So, and one thing here, whatever size of the code, 7,4. So you can observe 7 bits are there or not. Yes, 7 bits are there. Why? Because here we get the highest degree is P05. But we require 1 bit, so we place here 0. So it is a P6, but P6 is not there. So it is 0. Okay. Now coming to the systematic. So this is a systematic cyclic code. So what is a systematic cyclic code? So there is a procedure for generation of systematic cyclic code. Already we know. Again, we are going to use those procedure, and we are going to find the systematic cyclic code. Okay. So first step, we go to multiply. We multiply m of p by p power n minus k. I already told in cyclic code generation in theory. Okay, now in the problem also we follow the same procedure. First you go to multiply m of p. What is m of p? Message polynomial by p power n minus k. We know that n value and k value. You go to substitute. For example, in this problem, n value is 7, k value is 4. So n minus k means 7 minus 4. So you get pq. So you go to multiply the message polynomial by pq. Okay. So first step. Therefore, p power n minus k into m of p. So p power n minus p is p cube into, what is m of p? M of p is 1 plus p square. Why? Because we taken 1 0 1 0. Okay, so in this 1 0 1 0, 1 p term, p square, p cube. So what is the present? Only this 1 and p square. So 1 plus p square. For example, p cube also there. Then 1 plus p square plus p cube. For example, all ones. What you get written? 1 plus p square plus p cube. So this is my message polynomial for all ones. Okay. So in that way we are going to generate all the code polynomials from the given message polynomials. Why they are not given any one message polynomial? Find all the code polynomials for the 7,4 code. So 16 code polynomials you can generate by using that 16 message polynomials. So 16 message polynomials are similar. So we're not wasting our time. So I taken one example. From that example, we're going to find the code polynomial. Okay. So this is the first step. The first step, we multiply m of p by p power n minus k. So in textbooks, we may use x of p or 1 plus x. Anyway. Okay. Next, we divide by p power n minus k into m of p by the generator polynomial. Generator polynomial. So the given generator polynomial g of p. Okay. So for write this one, p power n minus k into m of p divided by g of p. This is my g of p, generator polynomial. Okay. So what you got? P cube plus p to the power of 5 divided by g of p. What is g of p? 1 plus p cube. This is the second step. Okay. So we could divide now. So p cube plus p to the power of 5. So p cube plus p plus 1. So same. So why here written p cube first? Showing the highest degree. Okay. Yeah. How many times you go to cancel this one? Or you can return this also same. No problem. What that one? P to the 5 plus p cube. Highest degree first. So then easily what you got the quotient easily. Okay. So whereas here p cube the left hand side and the side is the 5. So how many times? P square times. So p square quotient. So now we're going to multiply p to the 5 plus p cube plus p square. Okay. So here not an ordinary division. We are go for the XOR or modulo to sum, what it may be. XOR operation. So what do you XOR operation? 1 XOR 1. You got 0 this term. Plus again 1 XOR 1. 0. Plus here no p square term. So 0, 1. What you got? 1. 1 p square term. So this is my remainder. What my remainder? P square. So this is my remainder. So 0 having no value. So just left it off. So p square we got. Okay. Now coming to this, what you got the remainder? The remainder is p square. So this remainder which represents the parity bits. Okay, which represents the parity bits. So already we covered 3 steps. So 2 steps is covered. Now the third step. So in the third step, we are going to add this remainder term to the whatever the p power n minus k into m of p by g of p. So the second step, what you go to multiply and division. So we go to add this remainder term to the whole term. Okay. So we go to write p power n minus k m of p. So this is what you go to multiply message polynomial with the p power n minus k term. And now we go to add to the remainder. Okay. So coming to the this one. So what you got? P cube plus p power 5. This one. P cube plus p to the power of 5. Okay. So p cube plus p to the power of 5. But what are you going to add? Remainder. So the remainder having a highest term is square. So p square plus p cube. P square plus p cube. We got. So this is my core polynomial C of p. So now we have a doubt. In non-systematic, you have said there is no message polynomial or message vector you can't identify. But here you go to say you can observe this one. Now you are going to write this polynomial in a vector form. Okay, so one term is missing, p term is missing. We're having p square, p cube, p4 term is there. No, 0. 5 term is there. Yes. 6 term is there. No. No. So what is the total bits? 7 bits. So out of the 7, this one is the message 1010 and 001 is the parity. Okay. So this is parity bits and this is the message bits and this is my code. Okay, so in this way we can find all the code vectors for the given message vectors. So that's why the cyclic code is a subclass of block codes. So there is no difference between cyclic code and block codes, but the procedure is different. Okay, the pattern is different. That is similar. You can observe this message bits and parity bits also. Okay. Okay, coming to the another problem. For a 7,4 cyclic code, determine the generator matrix if G of P is 1 plus P plus PQ. Okay, here they given a clue. What the clue? 7,4. So my n size is 7, my k size is 4. They given GP, generator polynomial, but they ask generator matrix. Okay, so here n value is 7, comma k value is 4. So n minus k, what you got? 3. N minus k is 3. So what is G of P? Is 1 plus P plus P cube. This is G of P. So here they ask to build the generator matrix. They give a polynomial. By using that polynomial, you are going to generate the matrix, generator matrix. Okay. So for this, we given some cyclic operations. This generator polynomial is multiplied with the p term one time, and again p square G of P second time, and p cube G of P. Okay, this third term. Why we are going this, and later I go to explain. So first you go to multiply this of P G of P. Okay. So G of P is 1 plus P cube. So P into G of P. P square. Okay. And P to the power of next to P square term. So P square into G of P. P square, P cube, P to the power of 5. And P cube term. P cube, P4, P6. Okay, so now my G is equal to, this is my G. What is G? Generator matrix. So 1, P is there, again 1, P square term missing, P cube is there, P4 no, P5 no, P6 no. Next to PGP term. So 1 is missing, P is there, P square, P cube is missing, P4 is there, P5 missing, P6 missing. Next, 1 term missing, P term missing, P square is there, P cube is there, P4 missing, P5 is there, P6 is missing. And last one, for the last row, 0, 0. Why? 1 is 0. P is 0. P square is 0. P3 is there. P4 is there. P5 is missing. P6. So here, what is the size of the generator? 4 by 7. You got 4 by 7. Why? Again, you go for the block code. In block code, how to generate the code polynomial? You just multiply the message polynomial, message block with the generator matrix. So here you get it, C equal to M into Z. What is M? Message. What is Z? Generator matrix. You go to multiply, then you could generate the code vector or code block. Okay. Now here, after getting this G, the generator matrix, here you can observe any identity matrix there? No. So now we can say this is a non-systematic generator matrix. Now we are going to convert this non-systematic generator matrix into systematic way. Then we can observe the identity matrix. Why? Already you know that G contains identity matrix and quotient matrix. So G is equal to, in the form of IP or PI form. What is maybe? P is the quotient, I is identity matrix. It may be in the form of P argument of IK. So this is IK. What is K? Message block size. So in this problem they given 7, 4. So K is 4. So we can observe a 4 by 4 identity matrix in this generator matrix. When coming to this previous one, we can't observe the identity matrix. So now how to get this identity matrix in the given generator matrix? So by observing this generator matrix, it is in non-systematic form. So we convert this non-systematic form into systematic form. Then we can observe this G, identity matrix in the G. Okay. So to convert systematic form by adding the first row to the third row. So here we are doing some procedure. What the first one? By adding first row to the third row. We are having 4 rows. Okay. Second one, adding the sum of the first 2 rows to the 4th row. So we are going to do these 2 steps. For the first step, by adding the first row to the third row and adding the sum of the first 2 rows to the 4th row. Okay. So again go to write my Z 110 1 000, this one, and 011 01 00, and next 001 1010. Then the last one is 3 zeros 1101. Okay. So this is my non-systematic pattern of the generator matrix. So I am going to convert this non-systematic into systematic by giving the 2 steps. What is the first step? Adding the first row to the third row. So this is my first row. So this one is the first row. So adding the first row to the third row. So I am going to add this first row, whole row to the third row. Okay. So first I am writing the first row. 1, 0, sorry, double 1, 0, 1. These 3 zeros. Now we are lefting the second row as same. Okay. So 0, 1, 1, 0, 1, 0, 0. Now I am adding the first row to the third row. So 1, 0. So in this third row, the first bit is 0. So 1, 0. Go to XOR operation. Then 1. Again 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0. This one. Okay. Next, adding these 2 rows to the fourth row. So here adding means we're not adding this 1 plus 0 as 1, or by operating this XOR operation is better. Why? Because, for example, this also do, but 1, 1 you get 2. So again you convert this 2 into binary form, 1, 0. So we are using this 0 only. This go to carry. Okay. So for getting 0, by adding 1 plus 1 also, or XOR operation 1, 1 also get 0. You get only 1 bit. There is an ordinary sum operation, addition, 1 plus 1 you get 2. So this 2 again convert into binary form, 1, 0. And taking the last bit 0. So that is a lengthy process. This is the simple XOR operation. Okay. So 0, 0 XOR also 0. You know only 3 terms. One is 0 XOR 0. What the result? 0. 1 XOR 0. What is the result? 1. Or 0 XOR 1. Also same 1. And both are 1s. 1 XOR 1. The result is 0. Okay. So now adding this first 2 rows to the fourth row. So what are the first 2 rows? These 2. This is my second row. Now 1, 0. What you got? 1. Okay. So this 1 again add this the fourth row. So here also 0. So 1. Okay. Next 1, 1. What you got? 1, 1. 1 XOR 1. 0. So the result 0 is again XOR with the fourth row. So here also 0. So 0. Next, first row bit is 0 and second row bit is 1. So 0 XOR 1. What you got? 1. Okay. So the result 1 is XOR with the 0. So 1 XOR 0. What you got? 1. 1 XOR this one. And coming to the fourth bit, 1, 0. So 1 XOR 0, you got 1. Whereas the fourth row, again 1. So the result 1 is XOR with the 1. So 1 XOR 1, what you got? 0. And coming to the fifth bit, so 0, 1. So 0 XOR 1, 1. Again, the result 1 is XOR with 1. So what you got? 0. And fifth bit, sixth bit, 0 XOR 0. So 0. So this 0 result is XOR with 0. 0. Okay. And the last one, 0 XOR 0, 0. This 0 is again XOR with the 1. So you got 1. So this is my systematic G. Now here we can observe the ID matrix or not. See, this is augmented. This is my P and this is my IK. So yes or no? Yes. 1 triple 0 0 1 double 0 double 0 1 0 triple 0 1. This is my identity matrix IK. So IK is observed. So this is the systematic generator. Systematic generator matrix. Generator matrix. Okay. So in this way we are going to solve. Now the third one. So here find the systematic code word for a 7,4 cyclic code. For the message word is 1010 using generator polynomial x cube plus x plus 1. So in this problem they given directly what the message word and what is the generator, and here they given they mention systematic code. So systematic code, you know the procedure. Yes or no? What is the procedure? Having 3 steps procedure. First, we are going to multiply the message polynomial with p power or x power n minus k. So why? Because it's given in x form, not p form. So you follow this notation. Whereas in the previous, they given p form polynomial g of p. Now this is g of x generated polynomial. Okay. So for this problem, first you go to write what is n, what is k, and what is n minus k. So n is 7, k is 4, n minus k is 3. 7 minus 4 is 3. Okay. And here we convert this message word also in polynomial. Okay. 1010. So already told 1 x is there, no, plus x square term is there, yes, x cube term is there, no. So m of x is nothing but 1 plus x square. So m of x is equal to 1 plus x square, and g of x is equal to 1 plus x cube. This is my g of x. So find the systematic code word. Okay. So first you are going to multiply x power n minus k into m of x. So this is m of x. So what is x power n minus k? X cube into m of x 1 plus x square. So what is the result? X cube plus x to the power of 5. This is the first step. Go to second step. Divide. Divide this whole term x power n minus k m of x by g of x. By g of x. Okay. So x power n minus k, x power n minus k into m of x by g of x. By g of x. Okay. So x cube plus x to the power of 5. This is x power n minus k into m of x. Now g of x. X cube plus x plus 1. So how many times is go? Simply square term. X square. Okay. So x square, x cube, x to the power of 5. So same pattern, XOR operation. So x5 is there, x cube is there. So 1 XOR 1, 0, 1 XOR 1, 0. So what are the left? X square term is left. So just you go to add this x square term to the x cube plus x to the power of 5. Simply. This is the third step. Add the remainder. This is my remainder. Why? Because here the quotient remainder both are same, but don't confuse it in the procedure. So just add the remainder. Okay, add the remainder to this g of x term. Not g of x. Add the remainder to the x power n minus k into m of x. This is x power n minus k into m of x. This one. So add this remainder to the x power n minus k into m of x. Okay. So now convert this into code 001 1010. So this one. Right hand side is message, left hand side is parity. Okay. Now coming to the fourth one. So this is a little bit large. A 15,5 cyclic code has a generator polynomial g of x is equal to 1 plus x square, x to the power 4 plus x to the power 5 plus x to the power 8 plus x to the power 10. Find the code polynomial for the message polynomial m of x is equal to 1 plus x square plus x to the power 4. So here, whatever the size, here the procedure is same. So what is the procedure? The three steps. First, x power n minus k into m of x and divide the x power n minus k into m of x by g of x and add the remainder to the x power n minus k into m of x. So those are the three steps. So you go to follow. Then you can generate the systematic cyclic code. Okay. Yeah. So what do you do? First write what is n. N is 15. What is k? 5. So n minus k is 10. Okay. So here they given 1 plus x square plus x power 4. So that is no conversion is required. But for understanding, good write, no problem. Okay. So m of x is equal to 1 plus x square plus x to the power 4. So in message terms 1 0 1 0 1. Okay. 5. Given. Why k size is 5? K is message bits. So 5 message bits are there. 1 0 1 0 1. 1 plus x missing. So 0. X square is there. So 1. X cube is missing. So 0. X4 is there. So 1. Okay. So this is my m of x. X power. Now we go to multiply x power n minus k into m of x. So the first step. X power n minus k into m of x. So what is x power n minus k? X to the power of 10 into m of x. 1 plus x square x to the power of 4. So multiply. What you got? X power 10 plus x power 12 plus x to the power of 14. That's one. This is x power n minus k into m of x. Excuse me. So what is the second one? Second step is divide. So divide is x power n minus k into m of x by g of x. Okay. So what you got? X power n minus k m of x. X power 10 plus x power 12 plus x power 14. So in different ways you go to divide this one. No problem. Okay. G of x. 1 plus x square plus x to the power 4 plus x to the power 5 plus x power 8 plus x power 10. So here 10 is the highest degree, whereas in here 14. Okay. So how many times? 4 times. So x power 4. So here you go to multiply this x4 term. x4, x5, x6, x8, x9 plus x12 plus x14. So this one you got. So here again you go to modulo to sum or XOR operation. For bottom line having x power 4, whereas in Upper line 4 is not there. So 0, 1 we got 0, 1 you got 1. So this x power 4, x power 5, x power 6, x power 8, x power 9 and 12 is there and x power 10 is coming. This 12, 14 is gone. Okay. Now the highest degree term is 10. So you got to multiply for single term. It's enough. Okay. So again 1 plus x square plus x over 4 plus x over 5 plus x power 8 plus x power 10. Okay. So again XOR operation. So in the upper line 1 is not there. So 0, 1 you got 1. Similar x square. 4 term is there. So it is missed. 5 term is there. It's going to miss. 6 term is not there. So it's come. 8 term is going to miss. Again 9 term will come. 10 will go to miss. Why? 1 XOR 1. What you got? 0. So 0 in x power 10. 0. So what is my remainder? This term. This is the whole remainder. So second step is what? Now how to get third step? Add this remainder to the x power n minus k into m of x. That is the third step. Okay. So in the third step, add a remainder to x power n minus k into m of x. Okay. So first remainder is 1 plus x square plus x power 6 plus x power 9. This is my remainder. Now x power n minus k into m of x. X power 10, x power 12, x power 14. So this is my C of x, cold polynomial. 1 plus x square plus x power 6 plus x power 9 plus x power 10 plus x power 12 plus x power 14. Okay. So this is my C of x. Now let it see where is the message bits. Once again go to the message bits. M of x is 1 plus x square plus x to the power of 4. So already written 1, 0, 1, 0, 1. So this is my M of x. So by seeing this code polynomial, we can identify where is present. Okay. So let us write this code polynomial in bit form. Then we can observe where the message is. Okay. So 1 is there. So 1. X is there as x square as x cube. Missing 4. Missing 5. Missing 6 is there. Okay. 7, 0, 8, 0, 9 is there. Now 10 is there. 11 missing. 12 is there. 13 is missing. 14 is there. Okay. So what is the size? 15 comma 5. So now go to check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 bits are there. So this is out of 15. My message is only 5 bits. 10 parity bits are going to add. So coming to the right hand side, 1, 0, 0, 1. So this one. 1, 0, 1, 0, 1. So this is my message bits. And this is my parity bits. Okay. So this is my total code. Okay. So we're adding n minus k parity. Why? Because it is a 15 comma 5. 15 comma 5 cyclic code. So 15 minus 5, what do you get? 10. So n minus k is 10. So 10 parity bits you're going to add for the 5 message bits. So now it is easily identified and understand where the message bits are located. So I have to understand well. Okay, thank you. And the references for solving these problems taken from Simon Hacking, J.S. Chitodi, and digital communication by Sanjay Sharma. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.